Uh, okay, so welcome to this discussion on diffusion phenomena, and that will be part one of the recording. There will be a part two where I'll be talking about chromosomes, polymers, and entropy. Now, note that chromosomes, biology, polymers typically is taught in a chemistry course, and entropy, the physics topic. And I'm going to talk about that, but about that later. Basically, this is more about talk about my work and research, but before that, I shall give an introduction to what is chromosomes and polymers. But to understand the physics that I'm using there in this in the part two of my talk, which is actually about physics of life and my work, one needs some familiarity with the phenomena of diffusion of Brownian particles in a liquid. And in that, I shall give the introduction, the background physics, and in particularly, I'll be discussing random walk, Brownian motion, diffusion equation, Langevin equation, central limit theorem, and so on and so forth, and tell you how all these are connected. So basically, let's start. So when we are discussing diffusion, I have intentionally put uh, different topics which seem to be very different topics. The topic of a random walk. In random walk, one basically talks about a person or a drunken person who takes n steps, n being a large number of unit length starting from an origin on the right or on the left. Right, so a person can take a step in the on the right and then another second step on the right, so this is time, and then a third step maybe to the left, so he comes back at this point. Suppose each step is of length a, and then the fourth step can be in the right again. And what one discusses is an estimate of the displacement. So that's a typical random walk problem which is discussed. On the other hand, we also discuss on a separate course, sometimes in fluid mechanics, sometimes in statistical physics, about the diffusion equation. So what is the situation there? One basically has some liquid and there are particles suspended in the liquid, and there is a density gradient. There's a density gradient means it's a non-equilibrium situation, right? So in one end of the box of liquid, there are a high number of particles, suspended particles. Here the concentration of suspended particles is high, and on this side the particle is low. The basically the density of particles is low, and basically what happens is due to diffusion, these particles from the high concentration region, they diffuse to the low concentration region. And you might have come across the Fick's law, which says that the particle current density, the rate of particle moving per unit area per unit time, is proportional to, or is equal to, is actually should be proportional, and there should be a d for diffusion constant, is proportional to the gradient of the concentration. And the gradient of the concentration goes in this direction from low to high, whereas the current goes from high to low, and hence there is a minus sign, and the proportionality constant is called the diffusion constant, and this is the Fick's law. And you have come across Fourier's law also, where again there is a phenomena of diffusion, but that's heat diffusion, where on one side there is a high temperature and on the other side there's a low temperature. There is, so here there's a particle current, but in Fourier's law you talk about a heat current, and heat flows from a region of high temperature to low temperature, and there the current is proportional to gradient of the temperature. Here it is a gradient of the concentration of particles. So that's the phenomena of diffusion. So random walk, diffusion. And on the other hand, in your class 11, 12, or even in your first year, second years, you might have heard about the Brownian motion, where you have a Brownian particle, a pollen grain. Robert Brown observed it in 1827. It does random motion in a gas of sorry, in a liquid, in let's say water, and it takes random motion, right? So these are apparently three different things, but they're deeply connected. And that's what I want to talk about in the first part of the lecture. So what I'll be doing is reminding you or discussing random walk separately, diffusion separately, around 10, 15, 20 minutes of this, 10, 15 minutes of this, and Brownian motion. And then tell you how these apparently very different things are actually very well connected, right? And this Brownian motion major contributions was Einstein in 1905. It's that magic here where he also gave the principles of photoelectric effect and relativity. And the third work was Brownian motion actually, but we'll talk about it more later. Okay, so we begin with random walks, then diffusion, then diffusion equation, the Brownian motion, then connect them together. So let's start with random walks. So what is a random walk? As I already briefly told you, that suppose there is a person um, um, who's completely drunk, so he doesn't know whether he has to move right or left. He starts out from the origin, which is the bar, completely drunk state, and he takes either a step to the right or to the left with equal probability. Now, each of his step though is exactly of length a. So that's a simplifying assumption. So he is either moving a step a to the right or a step to the left, in which he has a net displacement of minus a. So in this random walk, and this is time, so here in this particular, so on day one, suppose he starts out and he moves to the right, step A, so he has a displacement of 2a, a displacement of 3a. Now he moves random d, which is uncorrelated. So every step that he is taking does not depend upon the previous step that he has taken. It's a completely random event whether he's going to move to the left or to the right, and that's the ideal random walk. So here his fourth step, let's say that he takes to the left, which means he comes back to position 2a, then comes again, takes a step to the left and then to the right and left and so on so forth. He keeps doing that. And here I have shown, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 steps. And in 12 steps, he has a net displacement of minus 2a, right? Now on day 2, he basically starts again from the bar and again starts, let's suppose, one step to the right, but then second step is to the left, and then again to the left, and then again right, and so on and so forth. And suppose after a certain number of steps, he basically reaches here, I don't know, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Again, there are 12 steps. And he has a displacement of plus a. Now, on the third day, he might again start out from the bar. And on this day, you see that he's moving a lot to the right. So 3, 4 steps to the right, one step to the left, then he again comes back. But finally, after quite a few steps, he has a net displacement of 5e, right? So the point is, we are going to ask, I mean, every day, suppose he takes n steps fixed, yeah, but on each day he is having different amounts of displacement, right? So the point to discuss is what, I mean, if he every day takes n steps, on an average, where is he going to reach? So that's a kind of step. Now, it is also possible that he takes all steps, all n steps, where n is large, to the right. It's not an impossibility. So the probability of one step moving to the right is probability half. Then the second step Again, going to the right is probability half. So the total probability that he takes two steps on the right, one after the other, is half into half. And if he takes all steps to the right, the probability that he will take all steps to the right is half to the power n steps all he has taken in the positive direction. Right? So that's a possibility. Now, if n is large, you can calculate that this is a very high probability. For example, if he takes 4 steps and he has taken all 4 steps to the right, the probability of that is 1 by half to the power 4, 1 by 16. And similarly, you can calculate if n is, suppose, 100, how small this will be, right? So that suppose there is a one rare day where he does manage to take all n steps to the right, and he manages to reach home. Let's assume that his home is to the right. But on many of the days, as you saw here, he's also moving out after 12 steps in the left direction, right? And here he's stopping after 12 steps at A. And if A is, and the number of steps is large, he can as well, with a very low probability, end up taking all possible steps one after the other, all to the left, and the probability of that also will be half to the power n. That's again a very low probability. Now, on an average, you would expect, on an average, if n is large, that one will take an equal number of steps in the positive and the negative direction. But will they be exactly equal? Unlikely. It's a random process, right? So if you flip a coin, suppose 50 times or 100 times, 100 times, are you going to always get 50 heads and 50 tails? No. No. Sometimes you'll get 47 heads corresponding to 47 steps to the right, and 53 steps, 53 tails, which means suppose 53 steps to the left. So there will be net displacement of -3. But your next day, yeah. So number of, suppose NP is the number of positive steps to the right, and N is the number of negative steps, to the left. A total is constant, positive, negative, total is suppose N. But each day you will essentially have a different number. Sorry. No, what happened here? Yeah, yeah. So on one day, suppose NP is 47 and NN negative is 53. On the day two, suppose this is 49 and this is 51. And suppose on day three, you have this to be 55 and this to be, let's say, 45, and so on. So total number of steps is different, but every day he's taking a different combination. He is not consciously taking, but he's taking random numbers. So the combination of NP and NN is going to be different, right? And he's going to every day end up at a different point in space away from the origin. Now, let's complicate the thing a bit more. Suppose if a person does 10 to the power 5 random walks. So basically, 1 lakh day, 10 to the power 5 days, every day he takes a random walk. And each day he manages to take exactly 10,000 steps. Now, n can be larger. But I'm just saying this so that you can visualize. The question we are going to ask is, where will he end up on an average? Yeah. So basically, you can estimate, or you can guess that roughly half of the days, NP will be greater than NN, and N is the number of steps he's taking to the left in the negative direction. And on roughly other half of the days, NN or NL left will be greater than NP, right? So in this case, the displacement will be positive. So on half of the days, displacement is positive. On half of the days, displacement is negative. And on an average, so if you take 10 to the power 5 random walks, if you average the amount of displacement over 10 to the power 5 days. Every day he is taking n steps, right? Np plus nn is equal to n. And every day you are calculating what is his net displacement after n steps. And now you are calculating what is the average displacement over 10 to the power 5 days, 10 to the power 5 random walks. Each random walk has n steps. Then you can guess that some will be positive, some delta x will be positive. So this is delta x for day 1, delta x for day 2, some are positive, this is delta x for day 3 and so on. So you are basically taking delta x for actually, so 10 to the power 5, so this should be 100k and an average will be 0. So average displacement in that sense will be 0. So average of suppose 100k random walks will be 0, right? That's something which you can intuitively think, right? But the point is, as we already said, sometimes NP is greater than NN, sometimes NN is greater than NP. Uh, yeah. So now let's ask a slightly different question. We have discussed all of this. So the displacement that the person reaches takes all steps to the right, so that he has a net displacement of NA, right, is half to the power n, and similarly minus NA is half to the power n. But suppose that he takes n minus 1 positive step and only 1 negative step, right? So the number of ways he can take all positive steps is only 1. So he has to take all the n steps to the right. But the number of ways that he can have n minus 1 positive steps and just 1 negative steps, there are many ways to do that. Why? There are actually n ways to have a random walk where he takes where np equal to n minus 1 and nn a step to the left. He takes only 1 step to the left. Why is that possible? Because it is possible he can take the first step to the right, then second step to the left, and so that's the 1 step to the left, and after that, thereafter, he takes all steps to the right. Okay? So that's a random walk, one random walk on a particular day, suppose 100 day. But on a separate day, he can also take the first step to the left, right? N equal to 1. The first step is to the left, and after that, n minus 1 steps he continuously takes to the right. So that's another random walk. Or he can also, what he can also do is basically, suppose he takes 5 steps on the positive direction, 6th step is in the negative direction, and thereafter all of them are in the positive direction. So these are all different kinds of random walks where NP is n minus 1. No? I don't know. Where NP is n minus 1 and n is 1. And there are n ways to do that. And thus, to have a net displacement of n minus 1a, there are n ways. Whereas all steps to the right, there was only one way, because you had to take each step to the right. There was no way that, yeah, I hope you get this. So in general, if NP plus NP plus n minus or n negative is a fixed number of steps, for a particular value of NP and NN, there will be NCNP. The C stands for combinatorial. So basically, what you are asking is, you're taking total n steps, but how many different kinds of random walks can be arranged if he takes NP steps to the right and N steps to the left, because he can take, I mean, just like in this case, one negative step could be had in different ways. Now, if you have two such negative steps and n minus two positive steps, where you place this two negative steps, right? You can place it in different ways among these, right? So you can have many ways to realize a random walk or realize a net displacement of n minus 2a. Here it is n minus 1a, but if n was 2. And in general, just think about it a bit. There are n, c, np ways of having different random walks corresponding to np, to a particular value of np. Suppose yeah, np is whatever 9,000 and nn is 1,000, so that the sum is 10,000. Then there are n factorial by np factorial upon nn factorial ways in general to have different kinds of random walks. So when n was 1, you can check, you can just substitute in this formula and see that there are n ways. So so this is how many different kinds of random walks you can have for a particular displacement. A particular displacement is decided by the values of np and nn. But the probability that a person is taking one of these random walks is actually half, because this is an unbiased random walk, 1 to the power np, half to the power n minus or nn, right? On the other hand, if it's a biased random walk, then the probability of np steps, suppose the probability of taking a positive step is p, and the probability of taking a negative step to the left is 1 minus p, then the probability of taking such a random walk with np positive steps and nn negative steps will be this, right? And in yeah. So in general, I mean, however, if it is an unbiased random walk, then this will be the net displacement. Now the question we are asking is a slightly different again, right? So see, if there are more ways of taking a particular random walk, and every day is a different random walk, the chance that he's going to take a particular random walk will depend upon the number of ways he can take that random walk. But the probability of each random walk, especially for an unbiased random walk, is always half to the power n. So the probability that a person will end up at a distance delta x, where delta x is np minus nn into a being the length of each step, is actually half to the power n, the probability of each random walk, right? Uh, I mean, of ending up at a particular random walk, and the number of ways that this displacement can be realized. This displacement can be realized in NCNP ways, NCNP ways, right? So the probability that a person will end up at a certain distance delta x is actually a product of these two numbers, right? I mean, here I have basically written down if np is 2 and nn is n minus 2, what will these various values be, you see? And you can see that as p goes from 2 to 3, basically this factor is increasing. See, n, right? So you can see n into n minus 1 by 2, n into n minus 1. Here there is n minus 2, 3 into 2. So this factor goes on increasing. It goes on increasing, this NC3 goes on increasing till NP equal to NN. When NP equal to NN, you have the largest number of ways where you can have a random walk. When NP equal to NN, remember, assuming the N is a even number, then essentially what you get is that the total displacement is zero, because the displacement is NP minus NN into A. The total displacement is zero, right? So the probability of any random walk, or the probability that the displacement will be zero, has the highest probability, because each random walk, each combination of, or in order, I mean, in the way you take a positive and a negative can be different. But for the same displacement, that is when NP equal to NN, then you have the largest number of ways you can arrange your random walk. You can arrange your positive, negative steps, and each random walk has probability half to the power n, because each step that he is taking either to the right or to the left has probability half, right? So this product will be highest when this number is the highest, because this remains constant, and this number is highest when NP equal to NN. And you can prove that. You can pick up any book on random walks or polymer physics. Why polymer physics, I'll come later. And the message is, where did it go? Yeah, the probability, the highest probability will be, so a displacement of zero, or NP equal to NN will have the highest probability, and it will have this value, because as NP keeps on increasing from 1, 2, 3, 4, this factor goes on increasing. But this is the highest when these two numbers are equal, and thereafter when NP becomes greater than n by 2, again this factor will keep on decreasing, right? Because of the symmetry in the denominator, it will again keep on decreasing. So what can be shown? So you can already estimate that when displacement is zero, you have the highest probability of having that the random walker, the drunk person, has the highest probability of finding himself near the origin, because an equal number of NPN, and then uh, and that is because that's the highest number of random walks he can take, whereas the probability that he will take all steps to the right or all steps to the left is very low. So you can already have a hunch that these values will be very low, these values will be very low at the middle. For delta displacement equal to 0, that is going to have the highest value when NP equal to NN. And so when this is equal to 0, displacement is 0. Now doing a bit of mathematics, and I'll tell you where you can look it up. There are multiple books on random walks, the multiple books, random walks in physics, random walks in biology. But I have looked up a polymer physics book because that's what I read. I'll tell you why random walks, how it relates to polymer physics right at the end of the lecture. It can be shown that this, when n is large, using some statistical physics, Stirling approximation, and so on and so forth. It's basically leads to how do you take log of factorials. You see, there's factorials coming in. There's a simplification which is done. That's what Stirling approximation. It can be shown that the probability, so I'm talking at the moment up till 1D, A random walk which has n steps and for which delta n, what is delta n? Np minus nn. So basically, the probability of a random walk with n steps for a particular value of delta n is, okay, I messed up the exponential here. There should be an exponential factor. I'm sorry. So 1 by root pi n e to the power minus delta n whole square by 2n. Right? That's a Gaussian. This is a function. It's a Gaussian in delta n. And if you add e square, so that's basically in terms of delta n, np minus nn. Now, if you add an a to the numerator and a to the denominator, then you get something like this. There's again an exponential missing because there's a Gaussian. That's what you get. And you already see that I have drawn an Gaussian function in anticipation. Now, this derivation I've left out. But basically what you get is then delta n a whole square is essentially delta x whole square. Uh, and this, if it's a Gaussian, you know that this would be variance, right? So what you essentially get, so I've set up the problem and just told you the result, not done the derivation. You can do it on your own if you want, looking up in a book or using Stirling approximation. So what you get is you are a Gaussian. So the probability that you will have a displacement of delta x with n steps, right? An n step random walk. Each step is of length a, is a Gaussian peaked at 0, right? And with the variance of delta x whole square average, that's the variance, displacement square, so displacement square expectation, average over 10 to the power 5 or whatever number of random walks, even higher number of random walks. The variance will be NA square. Now, the thing to note is, see, he has a person is taking n steps per day. But the standard deviation, so variance is sigma square, sigma being the standard deviation, the width of the Gaussian goes as root n. Standard deviation of the Gaussian goes as root n. Yes, if n increases, there are going to be larger deviations. Agreed, right? But the deviation is not deviation from the middle high point is not going as n. The deviation is going as root n. Right? And if you take variance or rather standard deviation by number of steps, standard deviation is root of this, of the variance. If you take standard deviation by n, what is the average number of steps? What is the width? N is the maximum distance he can move, right? And standard deviation is a width of this Gaussian, then that ratio goes as 1 by root n, right? So larger the number of steps, if you take this relative standard deviation by the maximum displacement possible, it is actually becoming sharper and sharper, right? So that's the message. So just for a random walk problem, I'm just summarizing. The variance is NA square, standard deviation is square root NA. The average displacement is 0 because half of the days is on the left and half of the days is going to end up on the right. But the right, most of the days is not going to be, I mean, this might be the peak. Note, this might be the peak. That has the highest probability. But most of the days is not going to end up here. He's going to end up here or here or here or here or here or here. That has the highest probability, but most of the days he's not going to end up here. He's going to end up on all of these days. So you see, integration of this probability dx is what is where he's going to spend the time. And if you want to say what is the measure, how far is he going to be, he or she, sorry, I shouldn't be whatever, gender biased, but suppose from the origin, if you want to take a measure of how, on an average, how far is he going to be found, so then delta x average is not a good quantity. Displacement average is not a good quantity, but displacement square average is a better quantity, and that is essentially the variance, and square root of that in terms of, this has dimensions of length, right? So on an average is going to be found root n a away from the point it is started. So these things I have already discussed. Now that is random walk. That's what I want to talk about random walk a bit more. Okay. So no, though we have been discussing random walks, this now actually connects up to something called a central limit theorem. What I said here is, okay, the exponential is missing here, but what I want to say is you got a Gaussian here, right? And I mean, basically, if you have a random walk problem, you will have this binomial distribution from which you get, for in the limit of large n, you can get a Gaussian which can be shown. But this can also be thought of or estimated if you know what is the central limit theorem. So random walk problem in some sense is connected to the central limit theorem. And let me tell why. That's because it's the law of large numbers. What is the central limit theorem or the law of large numbers? What it says that suppose you have a random number distribution. Okay, so D is missing here. Distribution. X1, X2, X3, X4, X5. From any distribution, it could be a Gaussian distribution or an exponential distribution, right? Or it could be a uniform probability distribution. So you have any random number between 0 and 1. So one value, so x1 could be 0.356, this could be 0.798, and this could be 0.124 or whatever, but this could be minus 0.589, right? So you have a sequence of random numbers. So basically, you have any random number which has a well-defined mean. Well-defined mean means you take n random numbers and divide by the total number of random numbers, and you get the mean of the random number where n is tending to infinity. And you have a well-defined variance. So suppose you have a well-defined mean and a well-defined variance from any random number distribution. What central limit theorem says that any underlying random distribution where a well-defined mean and a variance. Now, what is the distribution of the sum of n random numbers? Remember the random walk, every time he was generating going plus a or minus a. So those are the values of different random variables where it was allowed to take only plus a and minus a. And if you do a sum of random numbers where x1, x2, x3 can be any random number distribution as long as the mean and variance is well defined, then the distribution of the sum. So for day one, if he finishes the random walk, the sum of all the random numbers, n steps, 10,000 steps, is a sum. Day two, you have another sum. Day three, you have another sum. But there we were talking of random walks. Here we are talking, suppose there's any random number distribution and you generate n different numbers, calculate a sum, on you generate another series of random numbers, calculate a sum, day 3 generate another n random numbers, calculate a sum. As long as each of these random numbers are truly, each random day 1, day 2, they are independent. Random number by definition is independent, but I'm highlighting, I'm emphasizing that each sequence of random numbers from day 1, day 2, day 3, they do not depend upon the previous day, they are independent, but they're taken from the identical distribution. Then the distribution of x bar, the distribution of the sum is always a Gaussian. Okay. Independent of what the random number here is. In the random walk, it was only plus a and minus a. Right? There were two possible. What I'm saying that even if there are different kinds of random numbers generated from a Gaussian distribution, not all of the steps are equal. Or suppose from an exponential distribution. So the size of steps is not equal but decreases exponentially. But you generate n of those random numbers, sum them up, then the distribution of x bar, suppose you have 10 to the power 5 different sums, right? Then the distribution of x bar, so this is x bar, n is, I'm telling you that there are n steps or n different random numbers in a sum. So n different random numbers here, n different random numbers here, n different random numbers here. But the distribution of x bar will always be a Gaussian, yeah, where the value, I mean, so distribution will be a Gaussian where uh, it will be exponential x bar minus n mu whole square. So deviation from so the value of x bar which is deviating from n mu. Right? So what is this saying? What is the probability that you are going to have a particular value of x bar? So when you are doing a probability distribution, it's basically telling you what is the probability that you will have a value of x bar which is away from n mu. So this n mu is the mean of this Gaussian, right? So if you have x bar exactly equal to n mu, you know the probability. However, if x bar is different from n mu, you know, every day you're going to have a different value. We're asking what is the probability that you are going to have a particular value of x bar which may be different from n mu. So this is the mean, and the standard deviation of that Gaussian is going to be, or rather, you see, n sigma square is the variance, and the standard deviation is going to root n into sigma. What is sigma and mu? It is the mean and sigma square of the original distribution from where you were generating the sequence of random numbers. Right now, this is mathematical. But you'll see how it will link up to Brownian motion, to physics. At the moment, I mean, this is also taught in statistical physics, but just hold this, realize this, and I'll connect it up later. So it's basically, even if you have different number of, different size of steps, but mean of the random number distribution is defined, then if you take n steps, or rather you add up n random numbers, then the distribution of the mean will have this nature with standard deviation this, and the mean will be this, right? So in the case of random walk, the mean was 0. So that's why you had just delta x whole square. You didn't have a minus mu n, right? So that this would be that the sum of this random walk problem would be a Gaussian, even if you don't do this algebra, but if you know your central limit theorem well, you can figure out what is going to be the distribution of a large number of random numbers. So central limit theorem can be used also to study or understand the random walk problem. Right? This is the message. Uh, okay, so here actually I wanted to, before going to diffusion, I want to talk a bit more. So basically, just to give an example, that suppose you have a random walk. So see, previously you had a random walk with only +1 or -1. But suppose you have a random walk where each step is any number between 0 and 1. It can be 0.1 or 0.9 or 0.7 and so on and so forth. So then, so it's basically a random walk always to the right, say, any number between 0 and 1. And so we can calculate that the mean step size or the mean step uh, will be 0.5, right? Now, suppose you generate n random numbers, x1, x2, x3. So then you can ask what is going to be the sigma square, the variance of the original distribution, right? So I've just, so that you can get an estimate how to do it, this is not. So this is, I'm calculating the variance of the original distribution, right? And if you take n steps, then you can calculate what is going to be the distribution of the sum. Here I am calculating the distribution of the original distribution. The sigma square will be 0 minus 1 x, any random number, minus mu whole square. That's the definition of variance. And this is the probability that you are going, because this is a uniform random number deviate, dx by 1. Basically, the probability is dx by L because it's uniform random number. And if you do a bit of the algebra, you can see that the variance is going to be 1 by 12. Okay, so it's going to be 1 by 12. Let's change track. Let's talk about a different problem, diffusion. Okay, it's diffusion under concentration gradient. Now, you'll see how it is connected later. Now, here you are really talking about a box and there's a concentration gradient. Here there is a high concentration of particles. Here there is a low concentration of particles. Hence, the concentration gradient, the direction of the concentration gradient is from here to this direction, if you like, minus x direction, right? Where particles will flow. Particles will flow from the right to left. I mean, you have most probably this experience, because if left to itself, the particle concentration would like to become uniform. And the particle current, that is the number of particles per unit area. So number of particles flowing from right to left per unit area per unit time, right? And its dimensions will be n L square T per unit area per unit time will be equal to, so that's the Fick's law. And that comes from observation. There's nothing microscopic about it. It's a phenomenological theory. One sees, one has measured, experimentally measured, that this current is proportional to the minus grad C, opposite in direction, the proportionality constant, which was named the diffusion constant. It's a phenomenological quantity measured, experimentally measured. Fick's law, it is what is called. And there is, can see here, what have I written here? Yeah, so one initially has a concentration as a function of x and as a function of t, because if left to itself, the final concentration will become uniform, right? So it will evolve. It will evolve it from a non-uniform concentration as a function of time. It will become a concentration which is uniform. So C is a function of x and t. The other thing to note is dimensionally, this is concentration. Concentration has dimensions of n by L cube, and grad has dimensions of 1 by L. So you can estimate, or you can calculate that the dimension of d, the diffusion constant, has to be L squared by t. So this square bracket denotes dimension. I'm not saying it's equal. Here, the dimension of d is L squared by t. You can just balance out the dimensions on two sides, right? Now, that's called the Fick's law, but that's not the diffusion equation. Now, the conservation of mass equation, if you are in the second year or third year, you would have come across. So suppose there was a volume of liquid of density rho, and integral rho dV is the total mass of the liquid. Now, rate of change of mass of the liquid through this volume is equal to the flux. Sorry. So del m del t equal to minus del del t. So here I've written mass as integral rho dV, and that is equal to the flux current flowing out through the surface. Surface integral. If you integrate over the total current flowing out through the surface, and this can be written as using the, okay, whatever surface integral formula, Gauss and Stokes, I think Stokes formula. This surface integral over the entire surface can be written as divergence J. So basically, the mass conservation equation can be written as del rho del t minus divergence J, right? Now, this Jx comes because here we were assuming that the current is only in the x direction, but in general, you don't, you just have a divergence J. Okay, so here I've written in terms of rho, but here I had used C. Now, this is in general true, right? Particles flowing out through a surface. Here, the surface might be somewhere like this. So, Fick's law, there should be a vector sign here, J equal to minus grad C. Now, if you substitute this J equal to minus D grad C here, right? So del C del T or del rho del T, del C del T. So here rho equal to C. Go to minus divergence J, and J has been replaced here. Assuming D is not a function of X, divergence of D grad C, J was D grad C from Fick's law, you get this diffusion equation. This is your diffusion equation. And why do you care about the diffusion equation? Because on solving this diffusion equation, you will get concentration as a function of x and t. That is why you care, right? You framed up you basically got the equation from Fick's law and conservation of mass. Now, in Fick's law, you had two different quantities, J and C, right? That's not something you can exactly solve. But see here on left-hand side and right-hand side of the equation, you have C. You have a partial differential equation. Single derivative in time, double derivative in C. And you'll keep on seeing the diffusion equation in various contexts, in heat conduction, though here I'm talking about particle diffusion. Particle moves from a region of high concentration to a region of low concentration to make the to make uh, the concentration uniform. Now, when you have read about temperature T2 and temperature T1 and heat diffusing, remember externally there were conditions so that the temperature of T2 and T1 was forcefully held to fixed values. Here, nothing is being held to fixed values, or If you like, you could, if you put in particle continuously from the left, you could maintain the concentration gradient. So, but that's an external driving. Left to itself, it will become uniform, right? It will become uniform. And the evolution of this concentration gradient can be got by solving the diffusion equation. This is a combination of Fick's law and the conservation of mass. Just to remind you, so that you typically don't see all these different equations in the same page. One day diffusion equation is taught and some other day wave equation is taught. Just to remind you, wave equation is double derivative in time and double derivative in space as well. Here you had single derivative in time for diffusion equation. And the nature of the solutions of this is completely different, obviously, from the nature of solutions of diffusion equation. And of course, you have to give the boundary condition and the initial condition as well if you want to solve either this or that. Remember, how does Schrodinger equation? No, that equation is a single derivative in time and a double derivative in space, plus Vx and other combinations, right? So I've just wrote down different kinds, different equations which you most come across in physics so that you note the number of derivatives in space and time. But today we are discussing diffusion equation. Right, note the two minus signs cancelled off. There was a minus sign here from Fick's law and a minus sign here. So no, so it's a positive sign here. So now this is a PDE, first order in T and a second order in space. Now suppose, now that was maths. So basically you had a system, that, but then I converted it into a mathematical diffusion equation. Let's come back to nature. Now suppose in a huge drop of water, in a huge, I don't know, bucket of water or a jar of water, at time t equal to 0, you put a spot of ink, which means wherever that ink spot you put, call that x equal to 0, the origin. So you have a high concentration of ink at a certain point in space at time t equal to 0. Yeah. So you say that that is your initial condition. At time t equal to 0, at x origin, x0 being the origin, you have a delta function. That's your concentration. That's your initial concentration. And the question you are going to ask, now you know what is going to happen. The ink is going to spread, right? So the local concentration, the concentration of ink at x equal to x0, x0 being the origin, that is going to decrease and you're going to have more and more ink all around, right? Now, I'm again leaving you the mathematics. I'm just trying to give you the broad picture. The solution for CXT in 1D is again a Gaussian. So if you can solve it by Green's function or whatever mathematical methods, but I'm trying to build you making you familiar with the phenomena of diffusion. So what you're going to see is if you manage to solve it using Green's function, which will be taught in your mathematical methods course, if not already taught, I mean for the senior students, then you can figure out that C as a function of space and a function of time. Now you can also ask at a fixed time, how much has the concentration of ink molecules spread? Or you can say, okay, suppose at a certain point fixed in space here, at this point, x equal to 0, how does the concentration change as a function of time? Right? So this concentration, Cxt, concentration is a function of space and time. Note, there's a field equation. At every points in time, you have concentration defined at different points in space and similarly. So that will be something of this form. x square minus 4 dt. Note, this is again a Gaussian, but the variance 2 dt is the variance of a Gaussian, right? That has time inside it, which means that the variance is increasing as a function of time. So there's a Gaussian, but its variance as a function of time is increasing. So what would that mean? At time t equal to 0, it was fixed at a certain point in space. All the ink was here at x0. But over time t1, the variance is increased. This height would have decreased, which you can't see, but yeah. Over higher amount of time, t2, which is greater than t1, and so on and so forth. Yeah, it would have spread even more. It means that, so that's why, because it's spreading continuously, you see, its variance is increasing. Its variance is increasing. Moreover, you'll see there's a prefactor also. It's sitting in the denominator, means this is becoming bigger and bigger. Means at a certain point in space, if you look at concentration, it is becoming lower and lower and lower because the denominator is becoming bigger and bigger. Concentration at any point in space is becoming lower and lower. Moreover, the concentration spread about the origin is becoming broader and broader. And the reason it is becoming broader is the variance itself has time into it. This value is increasing. So it's getting more spread. So you have a Gaussian which is spread more and more and more. And at time t equal to 0, sorry, there is some problem. At time t equal to infinity, the variance will be infinity, which means it will be uniformly spread, right? So that's the solution of the diffusion equation, trying to make sense. I mean, once you get the solution, and getting the solution is a mathematical technique, but I'm trying to extract the physics of diffusion. If you had, I mean, here you had a problem which started out, you had a gradual concentration gradient, right? You had a gradual concentration. That's a different mathematical problem. You have the same diffusion equation, but your initial condition is different, right? Here, your initial condition was such that all the particles were fixed at one point in space at time t equal to 0. There, the initial condition is there's a concentration gradient. And there, you put in that initial condition and mathematically solve it, you'll see at time t equal to infinity, again, you will have a uniform gradient. But it won't be spreading like a Gaussian because you have a fixed gradient, right? Not localized in space. On the other hand, if you have something like this, on one side you have particles, on the other side you have no particles, then again the solution will decay. It's just a math, and you have the same partial differential equation, space-time dependent. You have to solve for it. You can solve it mathematically, or I have a computational physics course. At the end of it, there's some Turing problem, and there I have also shown how you can solve the diffusion equation, function of space and time, where you can even inject particles or you can inject ink at different points in space, at different rates, at different points of time. So more complicated. So those are different initial conditions, different boundary conditions. So these are simple boundary conditions which you can do analytically, right? But for more complicated systems, you have to do computationally. And those you can do by injecting different fluid particles at different times and so on and so forth. But talking about simple systems, if you have a concentration gradient like this, you can already most probably physically intuitively think that if there was a high concentration here and low concentration here, particles are going to diffuse from this region to here, from here to here. So particles, so basically the concentration here is going to become lower and lower and lower, and here the gradient is going to decrease. The concentration of particles here is going to increase, and finally you are going to have a uniform concentration. These are all solutions of the differential diffusion equation with different initial conditions and boundary conditions, right? Now you have this phenomena of diffusion, but one could also ask, what is the molecular basis of diffusion? That's Brownian motion, and we'll discuss Brownian motion next. But you know what, I think I need a rest. I'll continue on the Brownian motion and then tell you how all these things are related. When we discuss Brownian motion, I shall again invoke at some point random walk problem, right? Brownian motion is the molecular basis of the diffusion that we discussed here. So they are all interconnected. Yeah, but give me a break. I'll start again. Yeah, never mind.